just in general, the first episode is trying to get the Prime Minister of England to have relations, shall we say, with a pig on television. So, yes, don't watch that one.
Okay.
Yeah.
That's just weird.
It's a bad first episode.
That's something he would try to take to court.
All right. We're going to talk a little bit about algorithms. So I got a couple different algorithms. One of them, I just Googled bubble sort. I found one, right? There's all kinds of different versions of this. So not a big deal to find it. But we're going to talk about what bubble sort does, and we're going to talk about the function that I was talking about yesterday. So last time we had this function called calc. Right, so I call calc, I give it a pointer, right, to an array of characters. I give it a low value, I give it a high value. Right, so it does a couple things. And if we think about analyzing this algorithm, if we look at just this code right here, and we think about what is the time that code takes. When you talk about operations, it takes how many operations? About 2 or 3, right? Depending on like how you want to measure, right? Yeah, allocating, right? That always takes up time, but it's the same time no matter what. We got a comparison, we got some addition and assignment, right? So a couple of operations, right? Look at this. Okay, that takes 1. This takes 1, but then we have this part right here. So we're calculating what the midpoint is, right? And then we're going to do the calculation on the low side and on the high side, right? So unless low is equal to high minus 1, or high is equal to, low is equal to high, or sorry, low plus 1 is equal to high, right? So unless they're right next to each other, right, it's going to do this recursive call. Right? And on each recursive call, what are we doing to the size of our problem? So let's say we go 0 for low and 10 for high, just to make math easy, right? So what is mid going to be? 5. So then I'm doing the calculation on x, which is the same, right? X is never changing. 0 to 5 and 0 to 4, right, because it's mid minus 1, and 5 to 10. Everybody see that? Okay. So what are we doing to our problem on each subproblem that we're doing? Cutting it in half, right? So we've got 2 subproblems, and they're each half the size. Yes, Josh?
Why are we doing mid minus 1 and not just mid?
Why are we doing mid minus 1? So you can get into situations where, like, we don't want to analyze 5 on both sides. So we either do mid minus 1 or we do mid plus 1, usually. Right? Because if you look at what it's doing, right, it's just adding the actual character values and putting them in it. Right? So if we wanted to uniquely add up all of them, and we wanted to use this method to do it, this is not a very efficient method to do it, right? It's probably just easier to run an iterator over it. But maybe we wanted to find the largest value or something like that, right? The largest character value. So yeah, you're going to do it. There's going to always be like a plus 1, minus 1 sort of issue, right? That's also why this says is less than or equal to, in case we make a call where they're equal, or somehow we make a call where it's negative 1, right? Then we don't, high is smaller than low, right? We always want to be still in here. Okay, so then what would the runtime of this algorithm be? It's kind of hard to tell, right? If we don't have any good ways. I'll go to my browser, which only has 5 tabs open now. Make it 6. Dang it.
Here we go.
You can still read the tabs.
You can still read the tabs. Mill or dab, you can read that.
That's
Okay, so what we have is again, this is mathematical, but we're not going to go down the rabbit holes of all of these, like trying to do math. But so if we have a problem that is a recursive algorithm called T, and you're operating on a problem called N, we can break it down into A, which is the number of subproblems, right? So you see the A is in front, so that says how many subproblems do we have? T of N divided by B. So in our example, right, we have how many subproblems? How many times did I call the recursive function? 2. So A is going to be 2. And then we got N divided by B. So how much of a reduction in size did we do for that subproblem? We cut it in half, so B is 2. Okay? So and then it says plus f of n. So f of n is how much work did we have to do inside of the subproblem based on n. Now if we look at ours, right, was the amount of work that we did in the subproblem based on n? Right, so in this problem, right, if we go start at line 33 and basically go till line 40, right, any work that we would do other than recursive calls, it's not based on n, right? So it's O of 1, okay? Now, going through these, you might be like, oh, I don't know if I can figure these out. But we basically have to do a calculation on, so C, which is, did it show what C was? Oh, come on. Oh. So C is the runtime of the inner part, right? So it's that f of n. So we know that C is 1, and then if we take log base b of a, it'll tell us which one of these cases we have. It's kind of exciting, right? Not really. Okay, so log base 2 of that's a roundabout way of doing it, right? So we got 1, they're equal. So if we look, C is not less than log base b of a, so log base 2 of 2 in this example, right? B is how many subproblems we have. A is, anybody remember? B is how big the subproblems are. The number of times we do it, okay? So that's where we get log base 2 of 2. So in this example, right, they're both the same. It ends up that they're equal. So then you can go through here and figure out, okay, it's the generic form for this is n to the c log to the k of n. Okay, that's not exciting to look at. But they have a nice example here. So if we have, look at that, 2t n over 2, and then it says plus 10n. Well, we don't have the plus 10n. But it ends up that this is O of n log n. So even if we did n operations on that, we're only doing 1. But even if we were doing n, it would still be O of n log n. And they use theta. Right, so theta is exactly, right, so it's exactly n log n, as opposed to big O, which is no bigger than. So we'll always talk about big O.
So recursion is always in log n.
Well, but see, this in this example, right, we had so the subproblems were the same size.
Right.
We had 2 subproblems that were half the size. But if we had one subproblem that was half the size. Right, we go through our calculations and we'd actually end up with log n. So the one subproblem that's half the size is, suppose I have a sorted array and I want to find a particular element in that array. Right? So I take it and I divide it in half, right? I go to the middle and I say, is my thing bigger or smaller, right? Divide it in half again, divide it in half again. So I get to the end, right? So I had one subproblem that's half the size. If we go through that, I think we'd end up with, I think it's case 3, right? C is going to be greater than log base b of a, right? Because C is going to be 1, and we're going to be taking the log base 2 of 1, which I believe gives us 0, if I knew my logs right. So, that's right. Now, see, in this one, it was dominated by the n squared, but otherwise we'd end up with, maybe I did that wrong. C was 1. Is that right? No. Well, C is greater than, C would be, I think it'd probably still be this one, but that n is end of a 0, so then you get log n. Yeah, but so basically to boil it down, for the most part, the algorithms that we're going to talk about are going to be, I'm going to take something, I'm going to divide it in half, right? Each one is going to be half the size, and in general, I'm only going to do n work in that. So all the sorting algorithms that we'll talk about are going to run in O of n log n. Right, all the good ones. Right? The bad ones are not. We'll talk about bubble sort today. But let me work out that case. This is not maybe the easiest thing. Right? I just wanted to show this to you. Right? This is something that, I would go through and work on for graduate students, like making them go through and actually do all of the calculations, like give you a random algorithm. You have to figure out what the size of each subproblem is, plug it into the master theorem, and you'd end up right with a sort of runtime. The gist is that most of the stuff that we're doing is either going to be n log n, right? So if we're doing n operations and we're doing it log n times, that's good, right? For any sorting algorithm, that's about the best we can get. For terrible things, right, we'll end up with, n squared, right? Bubble sort runs n squared, depending on what we get, and we'll see why that is. So this is a way to figure it out. I'm not saying we necessarily need to do this all the time. But. Any questions on that in general? Or I'll work out the math on one of them and we'll talk about it.
I know the bubble sort is terrible, and you're not supposed to use it. But let's just say if I have an application, theoretically, like an array of 1,000 values, and it needs to be sorted, but I have like 2 days to solve a problem, why couldn't I use the bubble sort?
So you're saying, given a particular context, why would I not use bubble sort?
Yeah, if you
for
have
it.
enough time.
So there are legitimate reasons for using bubble sort. Like if you have a nearly sorted array and you just had if you have a sorted array and you add one element to it,
Yeah.
you can totally use bubble sort,
Okay.
right? And it's going to perform as good as most any other algorithm other than insertion sort might pick it up.
Yeah.
But so I guess the long and the short of it is pick the algorithm that is appropriate given what your n is, but you also need to think about the future. You said it was 1,000. What if in like 3 years that number becomes 10,000, right? Then all of a sudden your time is terrible. And by the way, you can just Google on a better sort and
Yeah.
right, just not pick the bad one. So there was a professor at Dakota State that told me the story about how 10 years ago, like he helped this company and they wrote this little tiny software program. And, you know, they had done exactly that thing. They said, oh, there's only like 10 things, right? We'll just use like bubble sort because, you know, it was fun and they decided to do that. Come back like 10 years later and they go and analyze the system and they just start talking to customers, which is one of the things that you want to do. And she goes, oh yeah, when we run it, you know, you start it and then you come back like 6 hours later and it's done. And he's like, really? You got that much data in there? So then they went back. All they did was change the algorithm that they used to do that sorting. All of a sudden it was like instantaneous. Because, I mean, they had like 10 or 100,000 things in there, and when he started, it was only a very small number. So some of it is you need to think about the future, but again, if you have a very limited scope, yeah, you can pick a particular algorithm and it's going to perform really well for you, and it's negligible or it doesn't matter, right? So, yeah. So let's talk about bubble sort. So last time we went to the algorithm visualization page, right, and we saw this thing called bubble sort. So basically what we have here is we start at the beginning, so that's our outer for loop, for c equal to 0, c is less than n minus 1, c++. Right, so that outer loop is saying, where am I going to start bubbling things? And right, things end up bubbling from the beginning, right? The biggest thing sort of, we keep swapping it until it ends up at the end. And then the next biggest thing, we start at the beginning, right? We swap until it ends up, the second biggest thing ends up at the end, right? And we basically do that, right? And this is the naive way to do it. And there's another way where you can check, did I swap anything? If we swapped anything, if we didn't swap anything, then we know that we're done. This one is just going to go through the whole thing. So if we think about how many times this outer for loop is going to run, how many times is that? N times, okay? So let's say n is 100, because math is easy, right? So it's going to go from 0 to 99. That's going to run n times. So let's say on the 0th time, how many times is the inner for loop going to run? C equals 0. I'll let you think. Tell me the answer. What? Well, if C is 0, N is 100, it's going to run 99 times, right? Everybody, does that make sense? We could draw a picture. Okay, so let's write this out. So we're going to, on the first iteration of this loop, C equals 0, we're going to run this loop 99 times, right? Then when C equals 1, we're going to run this loop how many times? 98. C equals 2, we're going to run it right? So if we add up all of the times that we're doing this, right? So anybody remember the summation that this is?
N times n minus 1.
You remember the result, right? This is actually sum of I equal to n. I is greater than 0. Where do I say it? Like I minus minus or something? I don't remember. Where do you write it if it goes down in the summation? Do you ever? Is that what we ever do? I guess we always write it the other way, right? You math people are going to correct me. I equal to 0 to n of I, right? And if we remember the shorthand for that one, as Jonah mentioned it, n times n minus 1 over 2. Right? Which is big O of what?
N squared.
N squared. Right? Because we ignore all of the smaller terms. The biggest term that we end up getting is n squared. Right? We have n squared minus n over 2. We ignore all constants. Right? So they just disappear. Right? So this is big O of n squared. Right? So not great. If we think about it. Right, and if we look on the inside, right, there's actually, if we count the operations that are in each one of these, we can figure out exactly how much it was. Right, we've got 1, 2, 3, 4 operations plus our check and our increment. So 4 plus 2 is 6. Right, so we would end up with 6 times n minus 1 over 2. And again, remember all of the, right, we can add those up, but if we look at that, that's constant, right? So it just sort of disappears, right? It doesn't matter. I could do 100 operations in there. Again, it doesn't matter because the runtime is based on how big n is. And so, to Spencer's case, right? You knew you had 1,000. It's 1,000 squared, right? So that's 1,000,000 things that you're going to do, right? 1,000,000 operations for an array of a size of 1,000. Well, so that's what, a quarter of a second or something, right? You can do 2 gigahertz, 2 million operations a second. But now if we just take that and all we have to do is multiply that by 1,000, and we end up with, is that a trillion? 1,000, million, billion, trillion. Right, so that's 1 trillion operations. So that's going to take, if we do 2, oh, thousand million, so gigahertz. That'll take a little bit of time. That'll take a couple minutes to sort, right? If we think about how many operations we can do in a second. So we went from like half a second to 500 seconds. So, does that make sense? Yes, no, maybe? Okay. So that's bubble sort. Let's see. Let's look at insertion sort. So like bubble sort is like the first one where they're like, hey, go make a sort. And they're like, here's how you can do it, right? And then people go and do it. And then they say, yeah, and that's like the worst thing ever. Don't do that. It's like derivatives where you like manually do it. And then they're like, oh, by the way, there's a trick. You're like, oh, that's awesome. You guys remember that? Right? Like they taught you the trick, and then you're like, dude, I don't have to do that stupid delta x thing. Right? Remember that? I always thought that was the coolest trick that like mathematicians taught me. Okay, so insertion sort. So let's see what it does. So they're asking at the top, they're asking for some information, right? They're scanning all the numbers into the array. Let's see. Oh, I don't know if I like this one. It's not very easy to read. Let's find a better one. You want the Rosetta one? This one looks at least properly named. That looks good. All right, so it says loop through all the numbers. So I equal 1, I is less than max, I plus plus, so that's going to run how many times? Max, which is going to be, I guess, our n, right? So we got an outer loop that's running n times. Then we are saying, okay, so value to insert is int array bracket I, right? So I is starting at 1, so it's going to start looking at the first location, right? Whole position. So basically it's going to try and find where does this thing need to go inside the array. Okay? So then it goes through while whole position is greater than 0, so I think 0 means something bad. It's going to start at whole position minus 1. So while that is greater than the value to insert, right? So we're going at that location, basically trying to find where do I need to insert this item. Right, so it's like when I would sort a list, right? I would go and find, okay, find where this thing needs to go, put it in that location in the list, right? So maybe we can, here, I'll grab this code. Let's see how it works. Okay, so it does a nice job of printing off all the things we have, right? So we have 4, 6, 3, 2, 1, 9, 7. So iteration number 1. So the item to be, so it's moving 6 into the right spot, right? So we got 3, 4, 6. Inserted 3 at position 0, right? So it found that 3 needed to go at the front at this point, right? So now we have 3, 4, 6, right? So the 4 and the 6, right, shifted over. So we got the sorted part is 3, 4, 6. And then the next iteration, right, we figured out that the 2 goes before the 3, 4, and the 6, right? The 2 got moved over, right? Then we found the 1, right? So if we're looking at the 1, well, we find that we have to put it at the beginning, right? And when we move one of these, right, we have to shift all of the other ones to their new locations, right? So if we think about that, if it's an array, right, we got to copy each one, right? So then iteration 4, it was looking at the 6, that was in the right location. Then we look at the 9, we find out where does the 9 need to go. The 9 needs to go at the end, right? And then I think it's going to check the 7, find out that it's in the right spot. Okay? Right, so it goes through and it's going to insert. So what do we think the runtime of this is? Better but not good. Right, so we know that the outer loop is n, so we've at least got n times that we're going to do it. So if we look at the while loop, I mean, it can have a range of times, right? Because the while loop, it's not a for where we're giving it a specific one. Check if previous number is larger than the value to be inserted. So what is the worst case time that this would have?
Trying to go through every condition, so max n.
Yeah, so in the worst case, right, it's going to be max. There are going to be cases where as it gets to the end, right, it's not going to change very much. Yeah, we still have n on the inside, right? This while loop can run n time. So we got n on the outside, n on the inside. What do we end up with? N squared. Right? I think if we make this backwards, so let's try making it backwards. So I need 7 numbers backwards. 7. Is that 7 numbers? We could do that. Right, so if we look at the number of operations we had completely backwards, right, so worst case for this one we have 2, and then 3, and then 4, and then 5, and then 6, right? So in the worst case, right, it behaves really terribly. Now, if we have a mostly sorted thing, right, it's mostly sorted, well, we really didn't have to do that much, right? So in a good case, it performs really well. So if you have data that's already sorted, right, the insertion sort is going to perform very well, right? Its operations are going to be, well, way less than that bubble sort, right? Bubble sort was, the n squared. This actually ran in n time, right? Because I only had to do one swap, right? The 4 and the 5, and actually I didn't have to do very much because they were right next to each other. Is this making sense? Any questions on it? So I've taught you really terrible algorithms, right? Right? So I think next time, we won't talk about it today. We don't have class on Friday. So on Monday, we'll talk about some of the better sorts. So for example, quicksort, right? And quicksort is going to use the fact that we can take a problem, divide it in half, right? And then sort the subproblems, and then we need to, did I say quick or merge? I said quick. Okay. First we'll look at merge sort, right? That's the easier one to look at first, right? So if we sort the two halves, right? So if I take a list and I divide it in half and I give one part to Forrest and one part to Stephanie, and then they give me back 2 lists that are sorted, then I need to merge those 2 sorts together. So we'll talk about merge sort. Quick sort is a similar idea, except for moving things around a little bit differently, right? But each one of them can break it up into a problem, give it to somebody else, and then take and merge the things together, right? And then we eventually, right, if they give me 2 sorted lists, I can very easily go through and just, okay, what's the smallest one? Grab it. What's the smallest one? Right? Just keep comparing until I get a fully sorted list. And when we do that, the worst case time for those is going to be n log n, because I divide the problem log n times, and each iteration, right, there's n work that we're going to end up doing. So I think that's all for today. Any questions? I'll probably issue a homework this week or next week. I'll let you know. You'll see an email on it. So you feel like next week? That'd be great.
Let's do it today.
What is your problem?